Hello. Now like to go over Riemann Zeta and the actual terms of it and what it really means and all that it's really saying in a nutshell. Um, in order to understand some of this lecture, it would be very helpful if you can go over my other lectures, particularly knowing why math is all relative, meaning that numbers themselves don't have meaning unless they're stated relative to something. In other words, the numbers that are written out, like 1, 2, 3, 4, and 5, all those numbers are relative to the number 1. Um, so they're all pretty much the same. 1 is 1 unit, 2 is 1 unit. 2 is 2 units, which would just be 1 unit and 1 unit. They could all be written relative to any unit that you want. But remember, when we just write a number alone, it means relative to 1. Because 1 over 1 equals 1, and 2 over 1 equals 2, and 3 over 1 equals 3, meaning relative to the number 1. Of course, also please go to my true meaning of pi video and to my exponentials and what they mean video in order to go through this lecture. So basically, Riemann Zeta is just in the same format, and if you go to my math paradox format, video, you can see that this 1 over x is the exact same thing that's being explored in Riemann Zeta, except it's 1 over ns, n to the power s. But it's the same thing. N to the power of s, I could have put x equals n to the power of x, n to the power of s, and I'd get that same 1 over x format, which is problematic in the language of math, and we'll review that quickly again. But basically, this is the function, and we'll go over that when we get to it in a moment. And of course, in math, the language allows us to count infinitely. And when we count infinitely, we put this symbol, an 8 on its side, or an infinity sign. And here are the problems in the language of math that we explored in our other videos, is that when we have a 1 over x kind of situation, we run into problems in our language because with a ratio and as a concept, 1 over 0 can be defined as the whole thing. But in the language, how many times 0 goes into 1, then we get a problem. Is it infinite? Etc. And please refer to my paradox video for the explanation of this. So in the language of math, this is kind of a problem. Again, these become problems as a ratio and as a concept. We have nothing works, but then if we have nothing divided by nothing, then we get another problem in the language. So this is why Riemann has problems at these values, because the language doesn't define really what they are. And as we saw in the other lectures, they approach 0 and they approach 1, and that's pretty much what's going on with Riemann. So particular values of Riemann, this equation is pretty much saying relative to 1, meaning that everything is going to be relative to 1. This n over s term is relative to the number 1, and this is written relative to 1. So again, please look at why we're going to be mixing terms up the way Riemann is written, and therefore the entity is not making sense. So if we look at this equation now, or this function, and we put s equals 0, so what we're saying is that for all these terms, n, now s, it's going to be 1 over n to the power of 0 plus 1 over, and this is going to count up. So it's going to be 1 over 1 to the 0, 1 over plus 1 to the 2 over 0, plus 1 to the 3 over 0. If you looked at my other video on exponentials, you'll see that 1 to the 0 in math is defined as 1, but it really doesn't have any meaning. And if you refer to that, it pretty much can be anything. Or it could be unity. It could be like a pi over pi. Well, that equals 1. Or infinity over infinity equals 1. Or x over x equals 1. So this term that it's coming out here is basically 1 plus 1 plus 1 plus 1 plus 1. We're basically sticking with unity the whole time. We're not getting anywhere. Or this could be pi over pi, 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 or x over x over x, or person over person, where just complete equality is being achieved. This is like pretty much the state of complete unity. And that's what this means, this state. It could be anything. This could even be nothing. It could be nothing because nothing over nothing is nothing, and that's complete unity. As long as there's not any inequality between the top and the bottom, we're fine, and complete unity is achieved. And unity is our non-dual state, and we'll go over another lecture I'll develop that describes what exactly that means. If we take a value of Riemann 1, then we go 1 over 1 plus 1 over 2 to the 1. This should be 1 over 1 to the 1 plus 1 over 2 to the 1 plus 1 over 3 to the 1 plus 1 over the 4 to the 1. And this means in terms of 1. And because our language goes infinitely, when you calculate this out, it'll slowly get larger and larger. And to the negative 1, well, in the language, it means 1 over 1 to the negative 1, 1 over 2 to the negative 1, which in the language takes the reciprocal of whatever this is. So it's 1 over 1 over 1, and 1 over 1 over 2. And that reduces to 1 plus 2 plus 3 plus 4. And, you know, again, I could multiply all these terms by a pi over pi entity, or an x over x entity, or an infinity over infinity entity, and then I'll get, you know, in terms of pi. So it'll be pi over 2 pi, pi over 3 pi, or vice versa. Pi over pi, 2 pi over pi, 3 pi over pi, 4 pi over pi. Now it's in terms of pi, or I can make it in terms of x. Whatever it is, and then, of course, I could count infinitely. So if I take all these together, then I'll get the answer will be pi over pi times infinity. Or this could be 1 times infinity. Or it could be x over x, which reduces to 1 times infinity. Basically, it just depends on what's relative to what. Going on to the next number, and this is where we'll start to see some issues here. Why math is mixing up terms, and why nothing's really converging to anything, because we're mixing up two different entities. So when we have Riemann value 2, and then we have this 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared equals pi squared over 6. It's saying it converges to this value, but we have to understand that these terms are all written relative to the number 1. And if you look at the math as relative, you can see that, you know, this is 1 relative to 1, this is 1 relative to 4, this is 1 relative to 9. And then we're getting this term, pi, which can never be an integer. By definition, it's never going to be an integer. And it's a ratio. So again, it's a totally different term. And it's being compared to something different, which is now relative to 6. So when we say it converges to this, we're totally mixing up our terms, because it's not converging to something that's related to this. It's converging to something of this nature, which is different. what we can do to make them converge to a similar entity is we can converge them both to our decimal system, which is based on 10 system. And then if we solve out these problems, and I showed in the other cases why 1/4 or 1/1 can equal 1 or whatever it is, that's unity. And then 1/4 equals 0.2500 or whatever, because 4 never goes into 1. It goes in 0 times. 4 goes into 10 1, 2 times. 2 left over. And with the rule of math, these are all rules, we take the leftovers, and then whatever's left over, we make another that times 10 and that times 10. So we make 20 more units because 4 can't go into 2. So we have to make 20 more. And how many times does 4 go into 20? 5 times. So 4 never went into 1, but it goes into 125 times. Or it goes into 1,000 250 times. And we did that in the other lecture, and we saw why this number really doesn't equal 1/4. So now I'm going to do, so pi squared relative to 1 is not an integer and never can be. What we could do is we can make a pi squared over pi squared, and then pi squared relative to itself is 1. Or pi squared over pi would equal 1 pi. And this way we'd be keeping our terms in the same language. So let's see when we get our value, which it comes out to pi squared over 6. And what we're going to do is we're going to examine that, and I'm going to write it out relative to 1. And when we calculate 1/1 squared plus 1/2 squared plus 1/3 squared, and we carry it out for the first 10 digits, we get 1.5496. And if I continued that on to infinity, it would approach this number. And then if I calculate the pi squared over 6 operation, and I also do that in terms of 10, then utilizing our rules, where all the leftovers then become 10s, in other words, 6 goes into 9 one time, there'll be 3 left over, and then I'm going to make 30 more, and then 8 of the other left over, and then 6 goes into 38 6 times, 6 goes into 26 4 times, and this is what this, now these two numbers are speaking the same language, so to say. So now we're in the same relative universe. We're comparing apples more to apples, although we could still never get a number that is going to make perfect sense, because pi is never going to be an integer to start off with as compared to 1. Pi is 3.141, and 1 is 1. And it goes 1, 2, 3, 4, 5. So how's a number that's a non-integer like pi ever going to work out in relation to 1 where they could be equal to each other? It can't. There's no way to do it unless I multiply it or unless I divide pi back by pi itself. Can I get 1? There's no other number to bring pi back into the integer realm. I have to use pi itself to get back. There's no integer. Pi over any integer, you will never get back an integer. Only if you do relative to pi can you stay in the language of pi. So we're mixing up the terms here. So what can I do? Well, let's look at this. I'm going to take this pi squared over 6 term that this function comes out to, and I'm going to multiply that by the reciprocal. And now I'm going to make this equal to 1. And then what I'm going to do is I'm going to take that same reciprocal and multiply it out by our function. And what I'll get is that 6 over pi squared plus 6 over, so this is going to be 6 over pi squared, and this is going to be 6 over 4 pi squared, and 6 over 9 pi squared, because this is 1/9 times 6 over pi squared. And I'll get these things, these values, equals 1. And then if I do carry out the math, I'll get 6 over pi squared and 6 over 4 pi squared, these values, and I'll calculate them out now relative to the decimal system of 10. And lo and behold, if I do it relative to now this new number 1, then these terms will then add up. I took the first 20 terms, and it comes out, I took rough numbers here. I didn't take all these numbers out, but if I had, it would have come out to 0.9999 as it goes to infinity, which will approach 1. So now I'm just going to solve the same equation for 1. Now we're going to speak the same language by taking this term and making it unity, and then taking this expansion and making it in the same language, which is a 6 over pi squared language. I'm taking an integer language and I'm converting it to the pi language so that we're talking the same language. And here I'm converting it to the tens language so that we're talking the same language. And then everything's going to converge to 1 when we convert everything into the same language. Here's the value for 3, which is 1.200205. This is Riemann value for 3. And if I take these values and I add out the first 10 terms, I get this. But if I kept going 1.164, but if I kept going infinitely, it would approach this number. If we do 4, then it converges, which we know it doesn't converge per se, because 1 can never be in the same relative situation as pi, because pi is not an integer. So it doesn't converge to an integer, it's converging to something completely different. But when we convert this number into a 10 system number, then we get this. And then if I rearrange our terms and say, okay, well, let's take that number, and then I'm going to take the term where, this Riemann Zeta 4 function converges to this. I'm going to multiply by the reciprocal, and now I'm going to make this equals 1, because this term and that term become unity. That crosses out, that crosses out, that crosses out, that crosses out, equals 1. And then I have to multiply our expansion also times the same thing. And when I carry out the calculation and convert it into decimal system, this would be 90 over pi to the 4th plus 90 over 16 pi to the 4th plus 90 over, and then 3 to the power of 4, which is 3 times 3 is 9 times 3 is 27 times 3 is 81. So 1 over 81. So that would be 90 over 81 pi to the 4th. And if I carry out these calculations in terms of the 10, and these are the this is the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 calculations that I've done here, I get 0.9939, which carried out towards infinity, it'll approach 1. So now I'm taking everything and I'm converting them into the same relative, so I can make a true comparison. You have to put it in the same language. I have to put this term in terms of pi in order to compare it to this other term, which I'm getting an answer in terms of pi. There's no way to compare integers to pi, because pi will never become an integer. It's 3.141, etc. It's in between numbers, and there's no integer that can ever give you back pi. Just like there's no pi that can give you back an integer. You have to divide by a factor of pi to get back and into the integer realm, because pi over pi equals 1 and 2 pi over pi equals 2, etc. So you can see how this mixes up all the languages, and nothing's really converging to anything. Here we have a value, Riemann Zeta 5, 1.0369, and here's our, here it is written out like in a division term, which we saw why this term doesn't really work very well, but utilizing it, we come up to this sum, and this is a value that we get if we do this, and it goes on, whatever it is. We do Riemann 6, and it converges to this value. And then if I convert this relative to our decimal system, I'll get this. And then we can do the same thing again. Okay, so Riemann 6 equals this value. I'll then convert this value into our integer system, and I'll multiply it by the reciprocal to bring it to 1. And in order to then convert this whole language into a pi system, I'll just multiply it by that same reciprocal, the whole term. So I'll get 945 over pi over 6 times, well, this is 1 over 1, so I'll get the same term. And this is 1 over 2 to the 6, which is 2 times 2 times 2, which is 8 times 2 is 16 times 2 is 32 times 2 is 64. So this is 1. So this is going to be 945 over 64 to the 64 times pi to the 6. And if I carry out these terms each time, I'll get these values, and that'll come out to 0.9997, which is going to approach 1. And so now we're speaking the same language. Here's for 9. This is just the value that's given. Here's for 10. We do the same thing. This is a converging value, although if I convert it to the 10 system, it doesn't converge. I get a number, which is written in the 10 system, whereas this is written in the pi system. And if I want to bring both into the pi system, then I take this value, that Riemann 10 equals this value. So to convert it to 1, I'll multiply it by the reciprocal, and I'll get then unity. So that'll equal 1 now. And then I have to multiply this term times each of these terms. And carrying out the calculation, this first term I'll get 0.9990. The second term I'll get 0.0009. The third term I'll get 0.000000000000000517, and again this will converge to 0.9999, which is going to approach 1. Now that I've converted everything to the same language, so nothing's converging here at all. We're comparing two different systems. So it's totally a trick. We're making this seem like it actually converges to a value. However, this value, for example, for Riemann 2, is not converging to this. These are two totally separate languages. And these are, this is generated using a Fourier transform, and then, going into trigonometric values, and basically just using other language to come up with a term and relate it in terms of these types of terms. But there's no other way to look at the equations except to put them into the same types of terms and to say that they approach a certain value when written in the same term. So in summary, Riemann Zeta is mixing terms. Pi, by definition, is a ratio, and if it's carried out mathematically in relation to the number 1, we're going to get a number about 3.141. If I carry it out in relation to pi itself, then I'll get an integer, like pi over pi equals 1. Or pi over 2 pi is 1/2, or 2 pi over pi is 2. In other words, it'll keep it in the integer realm, but anything else other than pi will destroy the integers. So the convergence is occurring relative to different variables completely. Therefore, there's no true convergence and there's no divergence. All the terms are being interchanged, and Riemann is just showing the two pure states that we don't have a definition for in the language of mathematics that I showed in our other math paradox video. And in our that 0 over 0 doesn't have a good definition in math. However, the concept of nothing, if I have no pizza and then I slice it up and I never slice it up, I'll be left with nothing at all. Or if I start off with one pizza and I never slice it, then I'll retain the whole pizza. But in the language of math, these two things have an issue. And so that's where Riemann is falling in between these two problems of math, 0 and 1. They can't be carried out. You know, in the way we're using the language, this 1 over x always causes a problem, and you can see that in the math paradox thing. So we're stuck to the same thing. And then primes, as I showed in the prime lecture, is just at what numbers unity comes back, utilizing the definition of what prime is. So if unity comes back, pretty much what's going to happen is we're going to get an average between this state and that state, and it's a trick that all primes, which are going to be unity, will then be the average between 0 and 1. Or we could say it's at 1/2. So that's pretty much Riemann Zeta, that this is the whole issue. In mathematics, we don't have a definition for that term, and we end up with these non-definable states at the 0 over 0 and the 1 over 0. When we try to divide, it doesn't work. We get our 0 or singularity concept, and we get our infinity concept, or our undefined, or whatever this is. And so that's it. When we say we converge or diverge, we have to remember that we are switching the terms around. We can't compare integers to pi, and we can't compare pi to integers because they're two different entities. And math is all relative to another entity. Numbers by themselves have no meaning. If I say the number 9 and I don't say that it's relative to unit 1, then it doesn't really mean anything. If I say the number 8 and I say it's relative to unit 1, then I can say 8. If I say the number 8 and it's relative to 2 units, then 8 can now become 4, because it depends how you wanna interpret it. But all these numbers are just shorthand versions. Instead of having to write this number out as 1 plus 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 1 9 times, I could just put that symbol and it'll mean the same thing. There's no magic about all this. This is all shorthand to help us with concepts that we've developed. And I thank you for your time.